So today I'm going to go over the Lasso code that we saw last week in class. So hopefully that makes it a little bit more clear on how to use the different arguments and functions that we saw in class. So let me just start with the code that I provided in the actual instructions. So this again just loads our data and creates our testing and training data set. And I'm going to jump right into the third question, which was about Lasso, okay? So as you can see here, basically we need to complete a bunch of code, okay? So the first thing that I'm gonna do is basically just take the code that I gave you for ridge regression, that I think just makes it easier. All I'm gonna do here is change the name, Lasso, and change, remember, alpha needs to be 1 in this case, because we're running a Lasso, not a ridge. So, great. We're almost set. The one thing that we need to do though is define what lambda sequence should be. So this is actually important because a lot of the times you don't know where your best lambda is and you actually need to find it, okay? So if you don't know, what you usually do is kind of cast a wide net of possible values and then kind of find a neighborhood where you think your lambda might be and then kind of narrow it down from there. So let's start with that. So how do we do that? We can provide a vector of lambdas that goes from 0 to 20. That's what this means, is a sequence between 0, starts at 0, ends at 20, okay? And a vector that's going to be length 100. So you can do length 100, or you could do something like by 0.5. So what does this do? Basically, it provides a vector that starts at 0, ends at 20, right? And has a step in between the numbers of 0.5. So let me just show you how this looks. Let me run that, lambda seek. So as you can see, it starts at 0, then 0.5, 1, and so forth until it gets to 20, right? I find it a little bit easier sometimes to just do length 100. You're kind of maximizing the number of values that you can get. So let's just do that. The difference here is that, again, it's going to provide a vector from 0 to 20 again, but it's going to divide that interval into 100 different bins. Okay, so let me just show you how that looks. Lambda sequence. So as you can see, basically the step is just a little bit smaller. Okay, so we're providing kind of a broader range, not broader, but a more granular range of lambdas. So let's start with that. That I think it's pretty wide. So let me run everything again. Remember to run it with the seed, and let's see how it looks. So as you can see here with the plot, we get that our first lambda is actually pretty good, right? We get an accuracy of about 87%, and then it clearly drops, and then it's basically the same, right? So this is kind of telling us that the best lambda is around here, kind of close to 0, right? And clearly under 1, okay? So what we can do is go back to our lambda sequence and now provide a much more narrow interval of values, okay? So I don't want to go from 0 to 20. I maybe want to go from 0 to, let's say, 0.4, okay? Let's try that one. And again, you can try different values, play around with it. I think that's always useful. And again, I'm not going to change the length. Now, the only difference is that it's going to take an interval between 0 and 0.4 and cut it again in 100 bins. So it's going to be even more granular than what we had before. So as you can see here, we basically have that the best accuracy is around here. I think that this looks pretty good, so I'm not actually going to tinker with it anymore. But again, you could, if you want, start finding something even more granular than this. I think that this is fine. So let me see what is actually our best lambda. So we can do lambda best tune, and as you can see, the best lambda is 0.004, okay? You can do also best tune lambda to be more specific, and you will get again the same thing, that's 0.004, okay? So that's great, we found our best lambda. Let's now see how this actually performs in our testing data set, okay? So remember that this was trained in our training data set, so now we need to predict how it would perform in our testing data set. So how do we do that? Remember that this is a classification task, so what we need to do is first predict our response, okay? So this is what this line of code does. So it takes the Lasso model that I just fitted, right? And then it predicts what the response or the outcome would be on the testing data set. So that's what's happening right here, okay? So as you can see, pred values is basically a vector that will take values of 1 and 0, That's it. Okay. So we can actually, if you want, you can do a table of pred values. And you can see that I actually predict 57 positive responses and over 2,000 negative responses. So those are my predictions. But again, I want to test how it actually pans out with reality, with the observed values. So how do I do that? I can compare my predicted values to the actual responses in the testing dataset. So this is what this does. Let me print out the head of this so you can see what this looks like. If that predicted value is the same as the response, then this is going to yield a true. If not, it's going to yield false. Okay. So as you can see, at least for the first 6 ones, all my predictions are actually correct. But remember that I want actually an average of this. Okay. And just for you to know, trues are considered 1s, false are considered 0. So that's how you can get an average of this. So let me get the average or the mean. And as you can see, is 87% basically, which is, I think, the same thing that you got with ridge regression. So it's actually not a bad model. Okay. Awesome. So we've got our performance, we've got our best tune. Let's now see how many variables did Lasso drop or did Lasso keep. Okay. So how do we do that? We can use this function here, which is called coef. Basically, what is returning is the coefficients or the betas of the Lasso model. Okay, and we provide basically the final model that we just got from the Lasso, and also the best lambda that we got. So that is why we also provide best tune lambda. So let's print this out. And as you can see, basically we drop some variables. We dropped this one right here, this one, and so forth, right? So there's some that we dropped. There's 2 ways that we can go about this. We can actually manually count how many variables are still left in there. The main issue is that is prone to mistakes. So there's actually a smarter way to do this. And the way to do this is basically save this line of code that we just created, this matrix or this object, into another object. So we're going to call it cofs, or you can call it whatever you want. I don't know, Lasso model, for example. So as you can see, Lasso model now is this kind of this matrix sort of argument. And P is actually what we want. So P right here, the second value, that 24, that is actually the number of coefficients that the Lasso model has. Okay. Remember that these coefficients also include the intercept. So we need to subtract 1 to this. So how can we do it? We can actually do Lasso, let me just put it here. We can do Lasso model at P. And again, we want the second value, 24, right? And we subtract 1 because we don't want the intercept. So let me see what this returns. It actually returns 23, so that is great. So basically, out of all the variables that were available, which I believe were 29 for this problem right here, it only kept 23. Okay, so it dropped basically 6 variables. Okay, so that is a way of finding out how many variables our Lasso has. Okay. So this is just to show you how this works. But again, finding the best tuning parameter, the best lambda, or for example, as we saw this week in class, the best complexity parameter for a decision tree, follow very similar rules. Okay, you start kind of casting a wide net of possible values, and then you kind of narrow it down when you found the neighborhood of where your best tuning parameter might be. Okay, so play around with this. Remember that your model can change, but usually the accuracy or the performance stays pretty much the same. Okay, so even though, for instance, if you had chosen another lambda grid, you might have gotten a different model, right? A model with less covariates and things like that. That is totally fine. The prediction, as you saw, is probably pretty similar between both. Okay, so that again can happen depending on how predictive your variables are or not. So play around with this, have fun with it. You will, if you're doing a prediction project, you're definitely going to be playing around with this sort of stuff. But again, get familiar with the code, all the things that you can get out of it, and reach out if you have any questions.